We're going to begin our formal study of limits today, and we're going to start off like we have always by building on a concept. So we're going to start off with our first concept. It says sketch the interval a to b on the x-axis with a point C inside. Again, here's our open interval. In this case, we will actually know a and b, and there's some point C inside the interior of a and b. Then what we want to do is find a value delta which is greater than 0. So there's a positive number delta such that for all x we have this statement here. This looks really ugly mathematically. It says 0 is less than the absolute value of x minus c is less than delta, implies a is less than x is less than b. All that says is if we find a delta, there should exist a delta such that the absolute value of x minus c, this means the distance between x and c is less than delta. However, this distance is also positive because we're dealing with an absolute value. If we can find this delta, then that guarantees that x falls between a and b. So we're going to start with our first example. We're going to choose a to be 1, b to be 7, and c to be 5. And we're just going to simply sketch our graph. Again, the goal here, and the goal in all these exercises, is to find the delta to be greater than 0. So here's our little open interval, and I'm going from 1 to 7. Remember, I want to find for every x in this interval, okay, or excuse me, I want to find a delta such that for all x minus c, or the absolute value of x minus c is less than delta, then that guarantees that x falls in this interval. Please note a couple things. X will always be inside this interval. That's our goal. Number 2, x isn't specifically c. We've marked a, b, and c here. A is 1, b is 7, c is 5. Okay. X doesn't necessarily have to be c. We just want to find a delta which guarantees that every x we plug in for this first piece guarantees that x falls between a and b. Alright, let's see what we have here. We have 3 points, and we know c is in the interval. So we can actually calculate this distance between a and c. Well, all your distance formulas, but on a line, we're not using our distance formula in 2 dimensions. We're using a single dimension. So instead of taking the square root of the difference of the squares, we are going to simply take the difference between a and c, the absolute value of it. So the absolute value of a minus c is 1 minus 5, which is 4. So the distance between the far left point and c is 4. Similarly, we can take the distance between c and b. This distance is 2. We now have 2 calculated distances. And the question is, which distance do we want? Well, again, we're trying to solve for delta. So we think about it. If we sit there and say delta is 4, well, if I start at c, because that's what this part over here says, the absolute value of x minus c, that means c is one of the points we're finding the distance between. If we start at c and go to the left, we get to 4, which is our a value of 1. Well, that still guarantees we're inside the original interval a to b. However, if we start at c and we go to the right 4, we are now outside the interval a to b. So therefore, if you notice that if we chose 4, we go outside the interval, we're going to actually choose 2, because if we start with 2 at c, we go to the left, we get to 3, and if we go to the right, we get to 7. Well, 3 to 7 is still inside the interval. Remember, we wanted to find a delta which satisfied 2 things. The absolute value of x minus c is less than delta, guarantees that x falls between a and b. So if I choose a delta of 2, which is the smaller of the 2 numbers, I guarantee that I fall inside a to b. Now notice I don't fall all the way inside of a to b. Notice my calculated interval, the calculated interval that I had for delta would be 2 would be 3 to 7, not all of 1 to 7. And so that's fine. So for delta equals 2, then for all x such that 0 is less than x minus 5 is less than 2, so if the distance between x and 5 is less than 2, that guarantees that x falls between 1 and 7. So now, what you should do at this point is pause your video and practice this problem. I will wait 10 seconds and then I will continue. We set this one up in the same way. We mark our A, B, and C. The distance between A and C is 3. The distance between B and C is 1. And we're going to use the same reasoning. We found our two calculated distances, so we take the smaller of the two calculated distances, so delta is 1. For delta equals 1, then x, such that the absolute value of x minus 5 is less than 1, implies that x falls between 2 and 6. Again, x falls between A and B. Now we're going to go a little bit different. We're going to expand this because we were just dealing with one dimension. We want to go with 2 dimensions now. Again, we want to find delta. It says find a value of delta greater than 0 such that for all x, 0 is less than x minus c is less than delta. That is the same part as what we already did. This entire piece up here is what we've already done. Now before we wanted to guarantee that x fell between A and B. Now we want to do something a little bit different. We want to guarantee that the absolute value of f of x minus L is less than epsilon. Well, let's study this real quick. Absolute value of fx minus L, that's a distance measurement again, okay? This was a distance measurement on the x direction. This is a distance measurement in the y direction, okay? This f of x, we're familiar with that. That's just function notation. This L, we've already started studying. L was the y value in our limits, okay? So f of x minus L is less than epsilon. Well, in this case, we're going to be giving you all this stuff except for delta. I'm going to tell you f of x equals 2x minus 4. I'm going to tell you c is 5. I'm going to tell you L is 6. I'm going to tell you epsilon is 0.2. Well, if we draw this, this should make sense because this red line represents our f of x function, okay? Well, here is our y value of 6. That is our L. Here is our x value of 5. So in other words, as x gets closer to 5, y gets closer to 6. That should make sense because that's what limits gave us were y values. Now, I'm going to add in some extra lines. Notice that this graph has changed slightly. I've added in these extra green lines above and below the blue line and to the left and right of this blue line, okay? Well, we need to make some calculations real quick. We knew this blue line up here was 6, and we need to find these green lines. Well, this is where the epsilon comes in at. We're basically going to sit there and take our L, which is 6, and we're to add and subtract epsilon. So here we start at 6, we go up to 6.2 and down to 5.8. What we've done is we've created an epsilon neighborhood around L. We're finding a neighborhood around L, okay? So as I get close to this L value, that's my epsilon neighborhood. And now we want to find a corresponding delta neighborhood. And the question is how we get our x markings. Well, this x marking, this blue x marking was 5. We already knew that from what we were given. However, the green x markings are what we have to calculate. And some people, the natural assumption would be, well, let's just add and subtract 0.2. We cannot do that because the 0.2 is an epsilon value, and we go back to our original equation, what we were trying to find, your epsilon was paired with your y values. Remember, the absolute value of f of x minus L is less than epsilon. So epsilon belongs to the y markings. The delta belongs to the x markings. Well, what we can do is we actually work backwards because we have this function here and we know the corresponding y values. So if I take my function, my f of x equals 2x minus 4, and we plug in for our y values. Remember, y is just f of x, and I plug in 6.2 and 5.8. If I plug in 6.2 equals 2x minus 4, I get x is 5.1. If I plug in 5.8 equals 2x minus 4, I get 4.9. So my markings, I have this 5, and then I have 4.9 on the left and 5.1 on the right. Now notice what we just did, okay? This gave us an open interval around C. This 4.9 is my A, this 5.1 is my C, is my B, and this 5 is my C. Now I have an open interval around C. And now we need to figure out the delta that we want to calculate. Now please understand, in your homework when you're given these graphs, they will give you all these markings. However, I want you to understand you can calculate them if you're not given them originally. So let's go back to what we were doing originally. We now have our A and our B and our C, and to find the delta we took the difference between A and B and the difference between B and C. So when I go to calculate this, we take the distance between A and B. That's 4.9 minus 5. There was our A, and there was our C, is 0.1. And the difference between B and C is 5.1 minus 5, which is 0.1. And since these are the same, obviously our delta is 0.1. And we make our statement. For all delta equals 0.1, For delta equals 0.1, then for all x, 0 is less than the distance between x and 5 is less than our delta, which is 0.1, implies that f of x minus L is less than epsilon, or in this case, absolute value of f of x minus 6, which is your L, is less than epsilon. Will epsilon ever equal delta? Yes, it will. And that will typically only occur when we have a linear function where the slope is 1. In this case, the slope is 2. And it shouldn't surprise anybody that our epsilon was 0.2, implied our delta was 0.1, because remember, your y, change in y, and over change in x, in this case, your slope is 2, so it shouldn't surprise anyone that epsilon is twice as great as delta. Let's look at another example. We'll do the same thing, okay? I'm giving you everything here. I'm giving you f of x is negative 3/2 x plus 3. I'm giving you c is negative 3. L is 7.5, and epsilon is 0.15. Now basically what we're doing, let's look at this conceptually. Basically your limit says as you get closer and closer to an x value, so here's your x value of negative 3, this is your c. So as x gets close to negative 3, what's happening to your y value? So in other words, if I'm within a certain distance, okay, if I'm within a delta distance of c, I'm approaching an epsilon distance of L. Or the proof actually, or the definition actually works backwards, that I should be able to find a delta, okay, a delta which is positive, so that if I fall within this delta neighborhood, I'm guaranteed to be within this epsilon neighborhood. And that's really all it's talking about, okay? Now please understand this negative 3.1 to negative 2.9 is not your delta neighborhood. This is your original A to B. Your delta neighborhood is usually smaller than that, okay? So we're going to not calculate the x values because we're already given them, but we're going to apply the same thing. Again, we want to find a delta. And the way we found a delta, we found first the absolute value of the difference between A and C. So this was negative 3.1 minus negative 3 is 0.1. And then we found the absolute value of the difference between B and C, which is again 0.1. So delta equals 0.1. And again, we finish off with our statement for delta equals 0.1. Then for all x, 0 is less than the absolute value. Notice this is x plus 3. It's not minus 3, because the reason it's plus 3 is because c is negative in this case, is less than 0.1, implies that f of x minus 7.5, or f of x minus L, is less than epsilon. This works for all functions, not just linear functions. Notice now I wind up with these crazy radicals, which shouldn't scare us away. We're going to do the same thing. We have our calculated neighborhood, our A to B. We're simply going to find the distance between A and C and take its absolute value, and the distance between B and C and take its absolute value. Notice I simplified this to decimals, make it a little bit easier. The distance between A and C is 0.118. The difference between B and C is 0.134. Again, go back to what we did originally. We take the smaller of these two, so we're going to take this 0.118. That is our delta. And basically all we're doing, notice I have this statement up here. I've had this the last few slides. All I'm doing is taking this entire statement right up top in this left corner, and I'm repeating it as my solution. Find a value of delta greater than 0. Well, we found delta. Delta was 0.118. So for delta equals 0.118, then for all x, 0 is less than, this is x minus c is less than delta. Well, I have x, I have c now, which is negative 1, so absolute value of x plus 1 is less than, there's our delta. I apologize, I'm getting email messages, so ignore those. Implies that f of x minus L is less than epsilon. So here is my f of x, here is my L, and there's my epsilon. Again, all I'm doing is taking this statement up here and I'm plugging in what I got for C, delta, L, and epsilon, and occasionally we will plug in for f of x, and we'll look at that in a second. So here's the definition we want to work with. Let f of x be defined in an open interval about c, except for possibly at c itself. Again, we're dealing with that open interval about c. We say the limit of f of x as x approaches c is the number L. We write the limit as x goes to c of f of x equals L. This should be very familiar to everybody. We've seen this statement already, and again, there's the familiar c and the L we've been dealing with. if for every number epsilon greater than 0, there exists a corresponding delta greater than 0, such that for all x, 0 is less than the absolute value of x minus c is less than delta, implies that absolute value of f of x minus L is less than epsilon. You need to memorize these last two lines. In fact, when you walk in the class on Friday or the next class period, I expect you to know these last two lines. Okay? And this is all we've been doing, really. We've been building to this in the first part of this lecture. And now we're going to actually see this work out and apply, and we're actually going to solve for this. Again, some notes. The epsilon neighborhood is around L, and it's going to be given to you pretty much all the time. You'll be given the L and you'll be given the epsilon, so you'll be able to calculate this real quickly. We're going to basically be finding the delta all the time. Okay, the delta is the neighborhood around C. Okay, so I have this vertical neighborhood around L. That's my epsilon neighborhood. I have this horizontal neighborhood around C, which is my delta neighborhood. We'll refer to the calculated neighborhood around C as A to B. We'll calculate it because it'll come from this epsilon neighborhood. Remember when we worked backwards? We took this upper value and got this B. We took this lower value, we got this A. Please understand the delta will be the smaller of these two distances. Remember that. This was our A and our B. This was our C, so we found the distances here. This delta will stretch the same to each side, okay? Now remember, it may not cover all of A to B, but it will go on both sides. All right, let's look at this now. Consider the function near x equals 1. It should be intuitive that y gets close to 10 as x gets close to 1. Remember we said when you look at a limit, the first thing we do is plug in. And so when we plug in 1, we get 2 times 1 plus 8, which is 10. The question is, how close to x equals 1 does x have to be so that y equals 2x plus 8 differs from 10 by less than 4? Well, let's take this and interpret it. This is what we've been doing. Our definition said the limit as x goes to c of f of x equals L. Well, our f of x should be obvious. This is just our y. Y equals 2x plus 8. Our L, well, we can see our L is 10 up here, okay? But if we go back to the statement, so that y equals 2x plus 8 differs. Differ means minus. So this is f of x minus from 10. Well, that's our L, because remember our statement was the absolute value of f of x minus L is less than 4. So your f of x is 10. The less than, there's your epsilon is 4. And how close to x equals 1? That's our c value. So now we have all the pieces in our definition except for the delta, and the delta is what we are going to be solving for. So now we're ready to set this up, and we're going to go back, and even though we're solving for delta, this is where it gets interesting, okay? We are not going to start with the delta piece. We're actually going to start with the f of x minus L is less than epsilon. And the reason we're going to start with this is that we actually know all these values. So here was our f of x was our y, minus L is less than epsilon. I'm going to go ahead and plug in for my f of x. So I have this absolute value of 2x plus 8 minus 10 is less than 4. Now we all know we can simplify this to 2x minus 2 is less than 4. Well, we're going to now change an absolute value inequality to a compound inequality. We reduce the stuff inside. This is 2x minus 2. And remember, the absolute value is less than 4, means that it falls between negative 4 and 4. So now I've gone from an absolute value inequality to a compound inequality. And these aren't difficult to solve for. We just have to remember that your rules for inequalities, especially compound inequalities, whatever we do to one side, we do to all sides. So I'm going to add 2 to begin with. Then I'm going to divide by 2. So I get this negative 1 is less than x, which is less than 3. I'm going to pause here because we just did something very important, okay? What we did is we just calculated our a, which in this case is negative 1, and our b, which is 3. If you remember, we looked at a epsilon neighborhood around y. Here was my epsilon neighborhood, okay? It fell between negative 4 and 4. We then solved those epsilon measurements and got our a and b. Now, we didn't necessarily want a and b. We wanted the distance between a and c and the distance between b and c. So this is what we're going to do. We know that c is 1. So we are basically going to subtract 1 from each side. Here is negative 1 minus 1, x minus 1 and 3 minus 1. If we think about this, this is our x minus c, this is our a minus c, and this is our b minus c. These are all important because x minus c, that was in our original definition. Remember, the absolute value of x minus c is less than delta. A minus c, well, that's heading towards the calculation of the distance between a and c, and this is heading towards the calculation of the distance between b and c. Basically, on this step, we're centering our entire argument around the c value. We're subtracting c from everything. This now gives us negative 1 less than x minus 1 less than 2, negative 2 less than x minus 1 less than 2. We can rewrite this as a compound inequality, and therefore we get our delta. This is our delta, okay? Delta is 2 in this case. Let's do another example, okay? A little bit more complex. Here I have limit as x goes to 2x squared equals 8. In other words, how close to x equals 2 does x have to be so that y equals 2x squared differs from 8 by less than 4? Again, working down, our f of x is 2x squared. Our L is 8. Our epsilon is 4. Our C is 2. And we're trying to solve for our delta. Let's go through the process again. We start again with the absolute value of f of x minus L is less than epsilon. We're plugging our equation. So 2x squared minus 8 is less than 4. Again, your steps are the same. We're going to go from an absolute value inequality to a compound inequality. We're going to solve. Notice we get the square root of 2 less than x less than the square root of 6. We need to understand this is our a and our b. And once we get to this step, this is the calculated interval around x. This is our open interval around x. We need to center it, or we need to subtract 2 from everything because 2 is our c. So now we get this negative 0.5859 less than x minus 2 less than 0.4495. Notice these numbers are different. So I can't just sit there and say, well, I can get an answer right away. We have to use a little bit of deductive reasoning. But we're going to go way back to what we did in our first slide. We're simply going to take the smaller of these two numbers. Okay. Now I have a lot of people jump and say, well, this is the answer because it's negative. Well, if you remember, we took the smaller of the absolute value of these numbers. Okay. Remember, distances require absolute values. So if I threw absolute values on these, the 0.4495 is the smaller. And therefore, delta equals 0.4495, or delta is square root of 6 minus 2. Let's get to what we really want to solve for, all right? Given delta, find delta given a specific epsilon. For the limit is x goes to 5, the square root of 2x minus 1 equals 3. Find a delta greater than 0 for epsilon equals 1. 0 is less than x minus 5 is less than delta, implies the absolute value of the square root of 2x minus 1 minus 3 is less than 1. This is what I told you to memorize. It's just with numbers plugged in. 0 is less than, this is x minus c is less than delta, implies the absolute value of f of x minus L is less than epsilon. So we're going to start off again. We're going to start off with this piece. There's the piece we want. Again, we're going to go from an absolute value inequality to a compound inequality. We're going to bring that 3 over to each side. We're going to square everything, add 1, and divide by 2. This again is my open interval around C. This is my A and B. And I haven't mentioned this yet, but we should be able to realize that we're on the right track at this point because the C has to fall between A and B. And if you remember, C was 5, so 5 falls between 2.5 and 8.5. So this is working here. And again, once I get my open interval, I subtract my C from everything. So C falls between negative 5 halves, or negative 5 halves less than x minus 5 less than 7 halves. Again, we look at the absolute value of these two, and the absolute value, or the smaller of the two, is 5 halves. So this is your delta. Delta is 5 halves. So let's see what we're leading up to. This should be very, very familiar to everybody, okay? Let f of x be defined in an open interval about c, except for possibly it's c itself. We say that the limit of f of x as x approaches L is the number L, and we write the limit as x goes to c of f of x equals L. If for every number epsilon greater than 0, there exists a corresponding delta greater than 0, such that for all x, 0 less than the absolute value of x minus c less than delta implies f of x minus L is less than epsilon. Let's look at the previous example. Here was our limit. Limit as x goes to 5, the square root of 2x minus 1 equals 3. Now we want to write our solution, and basically all we're going to do is take these last two sentences, which we've memorized, and we're going to plug in for c, delta, f of x, L, and epsilon. If for epsilon equals 1, because we were told epsilon is 1, there exists a corresponding delta. We solved for delta. We got 5 halves, such that for all x, 0 is less than the absolute value of x minus 5, less than 5 halves implies the absolute value of root 2x minus 1 minus 3 is less than 1. Please watch this and rewatch it. We will pick up here on Friday.